Okay, so we're going to now draw some of these so you guys actually know why these are important. Oh, there's water. Ooh, ah. Okay. Let's draw another one. This is just like boron trichloride on your lab. So what I want you to do is have notes out and also lab, because I'm going to reference the lab sheet probably every other slide. And if you guys are not here Friday, you got some lab stuff to make up quickly. So you'll pick right up there. Yeah. Yeah, we're gonna finish the lab today. Like I'm gonna probably hopefully talk for no more than 30 minutes.
Are we doing it individually or with other?
We'll get to it shortly. Probably in a group. Okay, so commonly boron is a smaller molecule. It likes to break the rules because octet rule is just a rule, not a law. You can break it. Boron trichloride. How did you guys draw this? I think Levi was the one who told everybody, right? So everybody that showed last week. What's the shape of this? Trigonal what? Planar, right? Because it's a flat plane. Right, trigonal planar, so it's a flat plane. It's not like a pyramid like ammonia is in H3 is a pyramid because it's got a lone pair on it. But boron has only how many electrons around it? 6, and it's happy with that, okay? Hydrogen's happy with 2, boron's happy with 6. Once you get to carbon, though, you got to have 8 or more. So this is fine here. But what are the bond polarities between boron and chlorine? Boron's electronegativity? I don't know this one too. No, electronegativity. 2.0. Chlorine is a 3.0. Is that right? So that's a 1.0 difference. So what would you classify the bond type as? Polar covalent. Okay, so polar covalent means draw dipole moments, right? So the dipole moment here points that way, and that way, because you're pointing towards the chlorine because it's more electronegative. So if you draw a big globe around here, that globe, are there opposite ends in terms of the charges? Yay or nay? Nay. Partially negative, partially negative, partially negative. Pretty much everywhere it's partially negative. So polar or nonpolar molecule? Nonpolar, not opposite ends. So nonpolar. So overall this is a nonpolar molecule. So can you have polar covalent bonds in a nonpolar molecule? Can you have, yeah, polar bonds in a polar molecule? Yeah. Okay, so it doesn't matter if the bonds are polar. It does not mean the molecular polarity is also polar. The geometry can do some cancellation. That's why we have to be able to visualize what it looks like too. And on your, there are 3 questions, I think there's 3, on your test where you have to, I'm actually going to have those molecules that you guys were building with, I'm going to build them. I'm going to set them on the lab station. So I'm going to say, okay, go to lab station 1 and identify the polarity of this molecule based on its shape. It doesn't matter what it is, you just got to be able to look at the shape and see if it's polar or non-polar. So that's why I'm letting you guys play with this so much. Okay, yeah, we'll do this first. So before we get to intermolecular forces, let's kind of revisit intramolecular forces. So I'm going to let you write down a little bit of this before I start talking. Write down what you need to, or just read. Oh, I'm passing out. I'm passing out the scantrons first on your test. The aqua colored circle number is your score on your test. Just FYI. Okay, so from what you can gather here, what's the difference between inter and intra, Lewis?
Intra is like small. That's for the atoms, nothing more.
Okay, so we're more related to the atoms bonded together. So if I'm an extrovert or an introvert, what's the difference? Extrovert. Means you're loud and crazy and you're interacting with others. If you're an introvert, you're kind of like, I'm gonna chill back here by myself and do this individually. So intra means within, personally within. Okay, this is personally within a given ionic formula unit or a molecule. Within a molecule, like the literal bonds between them, ionic or covalent. Inter, what's another word that uses the prefix inter? Interstate, between states. That's my favorite example because you guys know an interstate allows you to travel between two different states. So this is literally between two different molecules. Molecules, covalent or ionic? Covalent, right. So we're talking about the true covalent molecules and how do the two molecules interact, not within it, but between two different molecules. So we're going to approach these a lot today. I'm going to briefly remind you some of the properties of the covalent versus ionic because you have a quiz on that. It was supposed to be last week. I think I'm doing it review day, so Wednesday. And it's a Socrative quiz. It's one that you take online, so it'll be a quick response so you guys can know what to study. Okay, I'm only going to ask you to write two things. Ionic bonds. We already wrote down that they have ions, they transfer electrons, they're strong. Okay, how and why are they're very strong? They're strong because they have lattice energy that holds them together. It's an attractive component. It's called lattice energy. I'll show you a picture of a lattice in a second. So what I've got in green circled here is the important stuff because we already wrote down all this, like these properties related to it. The melting points are high, boiling points are high. They're electrolytic and they're aqueous, they're molten state. We wrote down a lot of that stuff. Now this part, the highlighter skipped here, but the part down here, it says charge product. That is the part, that's the math part of this. What you can do with this charge product thing is you can determine which type of ionic bond is stronger. So, sodium chloride versus magnesium chloride. Who's got the stronger ionic bond? Do you guys know? Got a 50-50 chance here. No, magnesium chloride, I'll tell you why. Okay, so charge product, here's how you do this. Charge product, I didn't expect anybody to say okay. Sodium chloride, magnesium chloride. Where did that two come from? Magnesium charge. Okay, what's product mean in math class? Multiplication. So charge product means multiply charges. That's all that means. So sodium chloride has a 1 plus charge and a 1 minus charge. What's 1 times 1? 1. Okay. So sodium chloride has a charge product of 1. I'm doing absolute value here. Magnesium chloride has a 2 plus times a 1 minus, because where am I getting the 1 minus from? Charge of chlorine, right? So that's got an overall of a 2. Oops. 2 charge products. So magnesium chloride has a stronger ionic attraction than sodium chloride. Give me an example of something that's stronger than magnesium chloride. Ionic bond. Go crazy. Iron what chloride? There's no such thing as iron chloride, but iron 3 chloride is stronger. Does it have a charge product of 3? What's stronger than a charge product of 3?
I'm sorry. Do I do another one?
Give me what you're going to tell me, and I'll adjust.
Oh, okay. Aluminum sulfide.
Aluminum sulfide, I like. Okay, so aluminum sulfide is Al. 2S3. Okay, so the charge product is 3 plus times a 2 minus, so that's a charge product of 6. What's even better? Give me a 9. Charge product of 9. Aluminum phosphide. Okay. What's the formula for that? Aluminum phosphide? Al what? P. All right. ALP. If I gave you that, I bet you 25% of us would go, oh, that's a 1 plus and 1 minus, because you wouldn't think about the charges that were truly there. But that is a charge product of 9, because aluminum is a 3 plus, phosphorus is a 3 minus, so it's a charge product of 9. So that's a really good example to me. Yeah. Aluminum dichromate? That would, a dichromate would have to be the anion, but that would only be a 6, because that'd be dichromate with a 2 negative charge. Turn that off. whoever's phone this wrong. Okay, so now let's talk about covalent. Covalent, we already know they share electrons. We already know they have pretty much opposite of all the physical traits, like, not soluble in water, low melting point, low boiling point. We know they have a shape. What are some of the shapes we know about covalents? Tetrahedral. What else? Bent, linear, trigonal pyramidal, trigonal planar. We know all kinds of shapes, right? So we already know all this jazz. Now, we need to figure out how to determine the strength of a covalent bond. If you're talking about just a covalent bond, you need to know the bond energy, which is on my next slide, or we need to know their IMFs. Oh, IMFs, that's intermolecular forces. That was on the last slide. First word up there, intermolecular forces. Those are called IMFs. So we're going to talk about bond strength and IMFs now. So if you're doing ionic, you compare those by charge product. If you're doing covalent, you compare those strengths by bond energy and IMFs. Okie dokie artichokes. Alright, that's a lattice. Ooh, ah. Ooh, ah. Okay, thanks, guys. Alright, so we already did this top one. Let's do covalent. The only thing that's new is this stuff right here. Bond strength and down. So it probably makes sense that covalent bonds, we know what single, double, and triple bonds look like, so we've built them and we've drawn them and everything. But it probably makes sense that a single bond is weaker than a double bond, but then a double bond is weaker than a triple bond. So that makes sense because you got one bond to karate chop, two bonds to karate chop, or three bonds to karate chop in order to break it apart. So the strongest and shortest is going to be the triple bond. And I tried to draw it here as I went. The single bonds are longer because their nuclei are not as close together between the two carbons. These are a little shorter, and then these are super duper short because they get closer and closer and closer as you add more bonds between them. There's no such thing as a quadruple bond. Okay, carbons can't. It's not that cool. Can't do that. What was the organic suffix for single bond, double bond, and triple bond? Huh? Those are the prefixes. Give me the suffixes. So, like we said, methane, ethane. What did ane pertain to? Which of those types of bonds? Ane. This is just a quick org overview as you summer writing. What's the next one? Ene. Ine. Why any ine? Be very specific. So if I said pentane, see? Pent, 5H, pentane. 1, 2, 12? Yeah. How'd I get 12? 2n plus 2 for the hydrogens. We'll work on that. That's very, very minimally on your test.
The E is 2n and then
Yep.
I is 2n minus.
Yep. This is 2n plus 2. This is 2n. This is 2n minus 2. For the H's. That's how you get the number of H's. We'll work with that. Don't worry. Don't stress. Yeah, most people do, because that's not something we talk about a whole lot. Okay, this is the big boy slide that we have, and then we're going to draw some of these and determine the IMF. So this is probably the most important slide I'm talking about today. And we'll practice these in the lab as well. And we'll keep passing out tests. Thank you for staying with me on Spring Forward Monday, because everybody lost an hour of sleep. You guys are on that struggle bus? Me.
Yes,
Huh?
oh, I forgot what it was.
Okay, I'm going to scroll down, and I'll come back up here to explain. So if you guys are writing more, go ahead and fill out the rest of the hydrogen. Told you this was the Oxford slide. I will scroll back down to this. Promise. I'll be back. Okay, so intermolecular forces. Another name for those are called the van der Waals forces, because Mr. van der Waal helped discover them, of course, so we like to name stuff after ourselves. The three from weakest to strongest are London dispersion forces, then dipole-dipole, and then hydrogen bonding. So this is the weakest up here, and these are the strongest down here. Don't forget, these are not simply covalent bonds or ionic bonds. They are present around molecules between different covalent molecules. So we need to know the abbreviations as well, because I try not to write up the whole shebang anymore. All right, so only nonpolar compounds will have London dispersion forces. Now, every single molecule technically can have London dispersion forces, but nonpolar ones have only LDFs. So give me an example that we drew in the lab or we did earlier in class that was a nonpolar molecule. Yeah. CF4, nice. Okay, so carbon tetrafluoride was one we did last week. And what's the shape of that? Tetrahedral. It's nonpolar because the fluorine, and fluorine all cancel each other's dipoles out, so it's a nonpolar molecule. So you would say CF4 and another CF4, they would interact via London dispersion forces. So that green dotted line that I'm drawing is a London dispersion force. It's a force of attraction. So what happens is there's some electrons in this cloud and there's some electrons in this cloud, and they kind of shift where they are located for just an instantaneous moment, and that causes a slight attraction. And the slight attraction is what the London dispersion force is. So you can probably imagine the more electrons you have shifting themselves around, they can possibly create differences in the charges, and that's going to create a stronger London dispersion force. So as you increase the number of electrons, or aka the molar mass is just called, I want to call it molecular mass, actually. If you increase the stuff, protons and neutrons, you usually increase electrons as well. So heavier things can have stronger LDF forces. All right, so now let's get away from nonpolar. If you have a polar compound, you can either undergo dipole-dipole forces or hydrogen bonding forces. But hydrogen bonding is a very, very special dipole-dipole force. That's only going to happen with specific bond types. So let's go up here. Give me an example of a polar molecule we talked about in our previous examples. Water. Okay, I like water. Give me more. More. That's like extremely polar. That's like ionic. That's like the most extreme of polar. Polar molecules, not formulations. Methane is actually going to be tetrahedral and they all cancel out. Ammonia? Did we draw that last week? Yeah? Maybe? Ammonium itself is going to be non-polar, yeah, because it's tetrahedral. So sometimes you get the hang of these at first, but if you look here, water looks like this. Okay, if I draw another water molecule, look what's really close to my hydrogen right there. What's really close to it? On the left leg, right here, or right leg. Oxygen with what? Lone pairs. These lone pairs here are slightly negative. This H here is slightly positive. So they create a slight attraction for one another, and that's going to happen over and over and over again, a million times in water. So this attraction from hydrogen to oxygen is called a hydrogen bond. Now, I'm saying hydrogen bond, not dipole-dipole, because, yes, dipole-dipole could occur because it's a polar molecule and they have attractions, but the special type of dipole-dipole force is called a hydrogen bond. And that only occurs whenever you have H's in the molecule bonded to F, O, or N. So I always say hydrogen bonds are fun. Yeah, they're super fun, guys. So hydrogen must be bonded with F, O, or N. And you can see in water, it's all jacked up now. Here we go. Water has an HO bond. What's this one going to look like? What's ammonia going to look like? HN bonds, right. It's going to have, give myself some space here. It's going to have ammonia with HN bonds. So this bond here is considered an HN bond. So it's classified as a hydrogen bonding situation because this nitrogen and hydrogen are going to be attracted to another nitrogen, hydrogen. So this nitrogen with a partial negative up here is going to be attracted to this hydrogen, which has a partial positive. So the attraction here is a hydrogen bond. So I say bond, but I don't mean a physical, like I'm connected to you. It's just an attraction. So a lot of times we say bond, they're flat lines. They're not actually bonds. So this is the strongest of all the IMFs because it's got the most, it's only because these are the most electronegative atoms or elements. That's the only reason they're stronger because there's a bigger difference in their electronegativity. Okay, but like I said earlier with the London dispersion forces, if you're comparing two different hydrogen bonds or two different dipole-dipole attractions, then you have to compare them based on their masses. So molar mass is increasing or molar mass is increasing. So let's try this baby out. Let's see what we got here. Get ready to draw. Oh, here's hydrogen bonding in action. Can you see it? They're shifting around, but this little attractive thing here. Ooh, ah. I have a lot of ooh, ah pictures. You know what ooh, ahs with me. Okay. Do not write this down. Talk to me. Do you think, knowing your strengths, do you think it's going to take more energy for me to pull apart water from another water molecule, or more energy for me to pull apart carbon dioxide from another carbon dioxide molecule? Why water? If I'm pulling water from water, or carbon dioxide from carbon dioxide. You said water. Right. Water has a stronger interaction. What interaction does water have? Hydrogen bonding, which is stronger than what interaction here? London. These are London dispersion forces because these are both nonpolar molecules. Nonpolars interact via London dispersion. So since London dispersion is a weak force, you can rip it apart pretty easily. Guess what? The air we're breathing, there's some carbon dioxide in it, right? We're breathing it out, we breathe it back in a little bit, we breathe it out. That's why London dispersion being so weak, it doesn't really hold its molecules together. There's carbon dioxide here, 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 and here. But water has a fairly strong attractive force with water, which pulls them together. Most of the time, water exists in what phase of matter? Liquid. That's why, because they're holding themselves together. That's the only reason it's a liquid. Thank the Lord, because we need water. We need it to be in liquid phase. Okay, so what I wanted to talk about that for is because if we're boiling water, it's going to boil at what temperature? 100 degrees Celsius. Boiling carbon dioxide. Anybody? Lower or higher than water?
Lower.
It naturally exists at a gas at room temperature, 25 degrees Celsius, right? Its boiling point is like negative 100 or something like that Celsius. So that's why I was talking about dry ice earlier, because dry ice is actually already in its gas, or it's in a solid stage, and it will boil in water at room temperature. I'll show you guys that when I get here, Steve, because I gotta get some. Okay, so this is what I want to accomplish today. I want you to draw, I want you to identify the IMFs, and this is what you're going to be doing in your lab. So let's take 10 minutes and do this. These you should be really good at drawing very quickly now. We're going to calculate valence electrons in our head. Okay, you probably have some of these already, so you can tell me what they look like. How many electrons are in NH3? 8 valence electrons. How many electrons are in water? Count up your valences. Valences is 8 again, because oxygen has 6. Hydrogen each carries 1 valence, so that's 8 valence electrons. How many carbon tetrafluoride? 42? 32, sorry. All right, let's stop there for a second. Let's go here. Dot structure. This looks like I've drawn this like 3 times today, so I'm going quickly here. That shape is a what? Trigonal pyramidal, good. Because it's got the lone pair up there, lone pair is pushing away, making it look like a pyramid. This shape. Bench. You've drawn water like 5 times today, too. So that's bent. This one? Tetrahedral. If you want to draw with me, that's fine. If you want to watch with me, because the new part's going to be these 2 pieces here. So I understand if you're a watcher or not a drawer. Okay, so I got tetrahedral here. All right, all of these are molecules because they're all covalently bound between 2 nonmetals. We got their dot structure. We got their we kind of know their electronegativity differences very little, but we have their shapes. That's basically what we need to know. We need to know their bond polarities here, here, and here. And we need to know their shapes before we determine their molecular polarity. So, molecular polarity, polar or nonpolar based on the shape? Polar, because there's a huge negative region up here, and there's a partially positive area down here. All right, this one? Oops, that F does not belong in there, sorry. Negative, positive, so this one's polar. This one? Nonpolar, because what? Because it's tetrahedral and the what? Dipole moments cancel each other out. Good. So there's dipole moments pointing towards fluorine on all of these. They cancel each other out, making it nonpolar. Okay? Based on your knowledge of IMFs, polar molecules can undergo what or what? Hydrogen bonding or dipole-dipole. Which does this undergo? Why? Right, because H bonds are fun. H to N bonds. Good. Next one. Hydrogen bonding because, same story, right? H is bonded to O. Next one. Why London? That's the only IMF that's related to nonpolar molecules. Correct. All right, so you have to know if it's polar or nonpolar before you can even determine the IMF. So that's, you just took your notes on IMF, so they should be right in front of you there. All right, so we're not going to do comparative boiling until we get through the whole shebang here. Next one, ionic or covalent? How do you know it's ionic? Magnesium is a metal. So you don't draw your Lewis structures here like normal. You draw them with a donation process. You show them donated. So magnesium plus chlorine, and there's only 7 electrons here. And there's 2 chlorines, right? There's 2 of those. So magnesium donates both of its valence electrons to both of the chlorines, making what charge for magnesium? 2 plus because it lost 2 electrons. And each chlorine now has octet. There's 2 of them, okay? That's what that 2 means. What's the charge on chlorine there? 1 minus, because it's only, each one chlorine is getting 1 electron. Okay, next one. Phosphorus 5 plus 21, 26 electrons. Okay, so phosphorus, chlorine, chlorine, chlorine. This looks just like ammonia, except it's got lone pair on all the chlorine. Shape. Trigonal. Yeah, you see the lone pair on top? It's pushing away the PCl bonds. So trigonal pyramidal. Nitrogen down here, N2. What does that look like? Triple bond, right. It's got a bunch of electrons between them. That one you drew in your lab. Last one? It's ionic, so you draw your little donation process again. This should be coming more quickly now because you guys have done this like a bazillion times. Na plus Cl with 8 electrons. Okay. Alright, so like we just did there, we determined molecular polarity. What's the molecular polarity of an ionic bond? Is it a molecule? No. So there's no molecular polarity there because it's ionic. Therefore, there's no molecular polarity here because it's ionic. It's not polar or nonpolar, it's ionic. Different, it's like the extreme polar thing. Alright, it also doesn't have a shape, so that's why I'm not going to indicate a shape here. PCl3, phosphorus trichloride, polar or nonpolar? Polar, because there's a huge lone pair up here, which is partially negative, leaving the rest of the stuff, you know, less partially negative. So that's going to be our more negative region. So it's opposite ends, polar. Next one, here. Is there any side with more? No? Equally sharing? So non-polar. So you have to look at the shape and the distribution of the electrons around it. Okay. Oh, this one does not have an intermolecular force, right? Because it's not a molecule. So it's ionic, as is this one. Doesn't have an IMF because it's ionic. So we need to assign the IMFs for these two. This polar molecule, London dispersion, dipole-dipole, or hydrogen bonding. Why dipole-dipole? Right. It's not nonpolar, so it can't be London. It's not hydrogen bonding because there's no H's bonded to bond, FO or N. Okay, this one? London. Okay, now the ranking process. What's the strongest of all bonds? True bonds. Ionic bonds?
Yeah,
Did we go over that? Okay. Ionic bonds are the strongest of everything, okay? They're top dog. Between these two ionic structures, we got sodium chloride and we got magnesium chloride. How are you going to figure out who's the stronger of the two ionic bonds? Charge product. Charge product of magnesium is 2. 2 plus and 1 minus is a 2. Sodium chloride, 1 plus and 1 minus is a 1. So who's the stronger? Strongest. Right. So this is number 1 in boiling point or melting point, whatever my top thing says. It's probably got a boiling point of like 4,000 degrees Celsius, okay? Like crazy, crazy high. Sodium chloride is going to be our next highest, so it's number 2 in our ranking system. It's probably got like a 2,000, 2,500 degrees Celsius. Crazy high, okay? Now we're covalent. Now between all the covalents, how do you figure out who's the strongest in terms of traction? IMFs, right. So strongest IMF type is what? Hydrogen bonding, so we're dealing with the first 2 up here. Yeah, first 2. Those are both hydrogen bound, hydrogen bonded. How do you figure out who's got the strongest hydrogen bond? Look at your notes. What did I say to do? Increases with molar mass, right, okay. Molar mass means look at the periodic table and add up their masses. What is nitrogen's mass? Look at the little number below it on the periodic table. 14. So nitrogen weighs 14. Each hydrogen weighs, hydrogen's mass, 1 each, so that's 3 more. So this total mass is 17 grams. Total mass of ammonia is 17 grams. Waters, each hydrogen weighs 1, right? So that's a 2 total. Oxygen's mass, 16. Carbon weighs 12. So that's 18 grams. So who wins?
Water.
Water. So water is the third highest boiling point. Ammonia is the next highest boiling point because we just went in order of hydrogen bonds and then you had to compare the two. Yeah?
Why is measuring grams?
It's actually in atomic mass units, but we don't think in atomic mass units, nor can we actually mass in atomic mass units. We mass in grams. So it's actually equivalent in terms of the conversion between atomic mass units and grams, which was like an extra credit question on your test. But now it's relevant. Okay. What's the next strongest after hydrogen bonding? Dipole. And there's only one contender here, so it's got to be number 5. Is that what I'm on? 5. Okay. So now between the last two, we have London. Those are London dispersion. They're both the weakest. Which is stronger of the two? Or how would you figure it out? You can count the number, not valence electrons. We just said electrons total. But I prefer to count up the mass because as you gain mass, you're gaining protons and electrons. So it kind of works itself out. So who weighs more, carbon tetrafluoride or nitrogen? Okay, it weighs 12 plus fluorine each weighs 19. So 19 times 4 is 76 plus 88, weighs 88 grams. So that's what I just say, 76 grams. So 88 grams there, and then nitrogen, 14 plus 14? 28 grams. Who's the winner? That's the winner of the weakest bonds. Yeah. So we're on red here. This is 5. This one's the next one, so it's number 6. And this one's number 7. Whew. All right, so we need to practice this in our labs. Okay, you see your lab sheet where it says IMF on the far side? So that's the reason I have to do all that with you today, because you need to do the math stuff. All right, so finish building today, and then you guys can do your finish off the columns as you go through your building process. Okay, so we have 30 minutes left. Let's get this party started. Bring in somebody who did not work with you last week, because I have 3 people who were absent last week.